Good morning. Good morning. This is Shivashankar Rajamani from KSR College of Engineering, Department of ECE. Today we will discuss about maximum power transfer theorem, a case study. Right? So we have a case study, a real-time application of power transfer theorem in 5G base station in the field of communication. This is the case. So we will first discuss what is maximum power transfer theorem. The statement, maximum power transfer theorem states that in a DC circuit, maximum power is transferred from source to the load when RTH is equal to RL. For applying this theorem, Thevenin's equivalent circuit is used, where RTH is equal to RL, which consists of a voltage source VTH in series with the resistor RTH, where VTH is the open circuit voltage at the terminals and RTH is the input or equivalent resistance at the terminals when the independent sources are turned off. So we have already discussed Thevenin's theorem. In this Thevenin's theorem, we found that VTH, or otherwise it is called as open circuit voltage, and we also found the RTH by removing the voltage source. If it is voltage source, we have to short circuit it. If it is current source, we have to open it. Then we have to find the looking back resistance or RTH. So maximum power transfer theorem, so that will have a combination of a VTH in series with your RTH, and you have a series with load resistance RL. This load resistance RL will be varying in nature. So we will be having a maximum power only at RTH is equal to RL. Again, the statement states that maximum power is delivered to the load from the source when the load resistance is equal to the source resistance or Thevenin's resistance. So we will be having the maximum power only when RL is equal to RTH. So we can find the current. So I is equal to, it is VTH divided by RTH plus RL. So just by Ohm's law, I is equal to V divided by R. Here your RTH and RL are in series, so we can add them both. So I is equal to, it's VTH divided by RTH plus RL. So introduction about the case, the maximum power transfer theorem states that maximum power is transferred from source to the load when load impedance matches the source impedance. So you must be asking a question, impedance. Impedance is the combination of resistance plus inductance, or resistance plus capacitance, or resistance plus inductance plus capacitance. So that is the practical thing that we are using. So source impedance is equal to the load impedance, then you will be having the maximum power. In the field of communication, this principle is crucial for efficient signal transmission in RF circuits, antenna and transmission lines. This case study focuses on how impedance matching is applied in 5G base station to maximize power transfer theorem and improve signal strength. So we go for the background or the problem statement. A telecom company deploying a 5G network in an urban area experienced a signal loss and an inefficient power transmission between transmitter and antennas. Engineers identified that the cause of the impedance mismatch between RF amplifiers and antenna signals, leading to poor signal strength at user device, higher power losses, reducing system efficiency, increased thermal dissipation affecting hardware longevity. To optimize the system, maximum power transfer theorem was applied to ensure efficient impedance match. So they found that impedance matching is the main problem. So because of the impedance matching, they found that poor signal strength, higher power losses, increased in thermal dissipation. So these were the case background power problem statement that they have identified. So the methodology used, system components analyzed, RF power amplifier, 50 ohm output impedance, antenna system variable impedance, you can vary depending upon the application. So fluctuation due to environmental condition also. So transmission line, which is a coaxial cable with characteristic impedance of 50 ohms. The measurement tool used is vector analyzer, which is used to analyze the frequency at which we are having the signal strength larger. To measure impedance mismatch, spectrum analyzer is used to signal strength before and after the mismatch. So this vector analyzer and spectrum analyzer were used to notify at which impedance it is being matched. Then power meters used to monitor the efficiency improvement. So methodology used. The steps followed is initially impedance mismatch analysis showed that antenna impedance fluctuation is between 40 ohms to 70 ohms causing reflection losses, whereas the impedance is only 50 ohms. The Smith chart impedance matching was also used to design a matching purpose. So here we could able to plot using this Smith chart to find whether we are getting the correct 50 ohms in the design. Observation analysis. So poor loss due to impedance mismatching. Before mismatching, only 72% of the transmitted power is reached the antenna, with a 28% loss due to reflections. The reflection is because of VSWR, which is approximately 2.0. So after mismatching, the power transfer efficiency is improved to 98% with minimum reflection, having this voltage standing wave ratio, which is approximately 1.05. The impact on signal strength. Before matching, signal received by the mobile user was very weak, especially at the cell edges. After mismatching, signal gain has improved from 3 to 5 dB, significantly enhancing coverage. Observation and analysis. Here we saw about thermal dissipation in power amplifiers. The mismatch system caused the power amplifier to overheat and reduce its lifespan of the components which is being used. With proper matching, power dissipator reduced by 30% and improving the reliability. So we can increase the life of the equipment which is being used. Results and summary. So we found that before mismatching and after mismatching, and what was the improvement. So power transfer efficiency before mismatching it was 72%. After matching it was found that it is 98%. So the improvement is plus 26%. Then voltage standing wave ratio. Before mismatching it was 2.0, after matching it was 1.05. Here you could able to see that improvement in losses was lowered. Then signal strength, so weak cell edge coverage issue was being found, that is before matching. After matching we could able to see that it is from plus 3 dB to plus 5 dB gain, which has the better coverage of improvement. Amplifier heat dissipation. So the device which has been used, which has been overheated because of before mismatching, which is high or overheated up. After matching, it was reduced to 30% and increased reliability of its improvement. So conclusion, by applying the maximum power transfer theorem, the telecom company successfully improved power efficiency, signal strength and hardware reliability. This case study demonstrates the critical role of impedance matching in RF communication systems, ensuring optimal power transfer from transmitter to antenna. Thank you.